So in this video, we're going to be looking at back titration, how we can actually do a calculation with it, and then look at the theory behind it as well. Now, starting off, right, in terms of back titration, you normally take some sort of an existing solution, or you take the mass of a certain solid, and then you dissolve it to make a solution in a volumetric flask. You take a portion of it out, and then you titrate it with known concentrations and known volumes of some sort of a usual base, or it could be an acid as well. Of course, you do titration, you work out a mean titer and whatnot, but then the theory is always going to be the same in that you're trying to work backwards and find an existing concentration or an initial actual mass or an MR or something like that as well. So yeah, starting off, looking at this question over here, we're told the student plans to determine the concentration in mole per decimeter cubed of ethanoic acid in a bottle of vinegar. The method is outlined below. First of all, we've got 10 centimeters cubed of vinegar. That's the first thing that we need to make a note of. So if I've got 10 centimeters cubed of vinegar, that's my first kind of point that I need to establish. That's going to be the end of my calculation because we're working backwards, aren't we? We're told that this is going to be diluted and it's going to be made up to a solution, a standard solution of 250 centimeters cubed. So of course, we're going to turn that into a solution. A volumetric flask is what we're going to use, and it's going to be having a volume of 250 centimeters cubed. Now, once we've done that, we're going to add the diluted vinegar to the burette and, of course, titrate 25 centimeter cubed volumes of 0.0450 mole per decimeter cubed barium hydroxide with the diluted vinegar itself as well. So you can see I've got my volume and I've got my concentrations given to me over here as well. Now, we're told that the mean titer of the diluted vinegar is going to be 25.45 centimeters cubed. And, of course, we've been given an equation as well. Now, what we can take from that is from that 250 centimeters cubed, we're actually reacting at 25.45, and then it's going to be centimeters cubed itself. So we're only actually using a small portion of this standard solution. Now, of course, right, that's our back titration step, and that's what makes it a bit more difficult. Now, the first thing that I need to establish is, because we're asked to find concentration over here, we have ethanoic acid to barium hydroxide. Our ratio is going to be 2:1 itself. We're also given some information about barium hydroxide and the volume and quantity of it. So that might be a good starting point if you're a bit stuck. So we need to find the number of moles, right, by looking at the volume, which is going to be 25 centimeters cubed of my barium hydroxide, and then I've got 0.0, and then it's going to be 450 as my concentration in mole per decimeter cubed itself. Now, in terms of this, if we're working backwards, because that's what you're doing back titration, we need to be able to calculate some moles of barium hydroxide. We then need to use some molar ratios to find the moles of course, ethanoic acid, and then our back titration step to find the original amount of moles that we had in 250 centimeters cubed. And then what we can do is we can actually find the concentration as well by linking that together. So starting with my calculation, then the first thing that I need to do is work out the moles of barium hydroxide. How am I going to do that? Well, I just take the concentration and times by the volume as mentioned before. So I'm going to have 0.0450, and I'm going to times that by my volume of 25 over 1,000 to convert it as well. And what I end up with to begin with is 1.125 times 10 to the power of minus 3 moles. So I've got my amount of substance in moles of barium hydroxide, but remember it's a 1:2 ratio. So to find the number of moles of ethanoic acid, CH3 COOH itself, but in 25.45 centimeters cubed, because that's the amount that we're reacting. Remember, that's what we said over here. We know that we're going to do the, of course, molar ratio 1:2. So I take 1.125 times 10 to the power of minus 3, and then I'm going to times that by 2, and that gives me a value of 2.25 times 10 to the power of minus 3 itself. So that's how many moles of ethanoic acid I've got, but more specifically, how many moles of ethanoic acid I've got in 25 centimeters cubed. So we've done this first step. This second step over here, we're about the moles in 250 centimeters cubed. Well, if we know that in terms of 25.45 centimeters cubed, we've got 2.25 times 10 to the power of minus 3 moles in that volume, right? If I've got 250 centimeters cubed, I would have a certain number of moles with the concentration of the rest of the volume being the same in that volume. So in that case, to find the number of moles of CH3 COOH in 250 centimeters cubed. This is a bit that's confusing for a lot of people. What you would need to do is you need to take a number of moles into 25.45 centimeters cubed, so 2.25 times 10 to the power of minus 3, and you're going to divide that by a value in terms of the volume which you've got, which is 25.45, and what that gives you is the number of moles you've got in 1 centimeters cubed. Now of course, if you find the moles that you've got in 1 centimeters cubed, you can then times by the total volume that you've got to find the moles in 250 centimeters cubed. So in that case, you divide by 25.45 times by 250, and what you end up with for the number of moles of ethanoic acid in 250 centimeters cubed is 0.0221, and then of course we're going to leave the rest of our answer in our calculator, and that's how many moles you've got. So far we've worked out the number of moles of barium hydroxide, we found the number of moles of ethanoic acid, and then the number of moles of ethanoic acid in 250 centimeters cubed. Now we need to find the original concentration of ethanoic acid. But remember, if you were to dilute something, so if you were to have, let's say, 1 mole over here and then dilute it into this new solution, you would still actually end up with 1 mole, but it would be less concentrated, it would be more dilute. So in that case, we're going to assume that the number of moles of ethanoic acid is going to be 0.0221 ... So in that case, to find the concentration of ethanoic acid then, so CH3COOH, that's going to be equal to the moles, which is going to be 0.0221 ... divided by the volume, which is 10 centimeters cubed now, because of course if I wanted to find the concentration in 250, I would just divide by 250 over 1000, but because I'm trying to find the concentration in 10 centimeters cubed, where the moles are the same in both of these containers, because this is dilution, this part, I'm going to have to take 10 and divide that by 1000 itself. So I'm going to have 0.0221 ... divided by 10 over 1000, and I end up with, putting that in my calculator, a value of 2.21, and then it's going to be mole per decimeter cubed to 3 significant figures as well. And you can see here my working out in full. I've labeled everything, everything's nice and clear, and if I get the final answer wrong, at least I get 3 error carried forward marks. If I get the first answer wrong, I get the 3 error carried forward marks. Still, it works in the same way. Now I've got one for you to try using the same steps, might be slightly different at the end, but I want you to pause the video, have a go at the following, and then we'll work through it once you resume it. So in this case, we've got a student and they dissolved 2.794 grams of acid HY in 100 centimeters cubed of water. So we've got a solid that looks like this, and we've got 2.794 grams of it. Now what they've done is they've dissolved it in water, and they have added a further 150 centimeters cubed of water, and they've made a standard solution of this as well. So again, I'm going to draw my little standard solution bottle, which kind of looks a bit messed up, but it will do. And yeah, we've got 250 centimeters cubed. It could be anything though. And what they've done is they've reacted 25 centimeters cubed of this time. So they've reacted 25 centimeters cubed of this time against sodium carbonate, and they used 23.45 centimeters cubed of sodium carbonate with a concentration of 0.0614 mole per decimeter cubed itself. So you can see here we've got some information regarding sodium carbonate as well as our HY acid. And now we need to work backwards, so we need to find the moles over here. We need to find, of course, the actual moles over here, that's the second part, then the moles in 250, and then with that we can use this to actually find the molar mass of HY, which is what the question is asking for. That's going to be part 4 itself as well. So yeah, of course we have here a neutralization reaction, we've got titration again, back titration, but this time we're trying to find the molar mass, the MR of HY itself. So yeah, the first thing that I'm going to do is of course work out the moles of sodium carbonate. So the number of moles of sodium carbonate, Na2CO3, is equal to concentration times volume. It's going to be 0.0614 times by, and then it's going to be 23 0.45 over 1,000 itself. Of course, I put them in my calculator and I end up with 1.43 ... times 10 to the power of minus 3 itself. That's how many moles I've got, and then that's my first step done. Now my ratio is going to be 1 to 2, right? Because of course we need to use our molar ratios here. So in that case, to find the number of moles of HY, but we're going to look at a volume of 25 centimeters cubed. So I'm going to state that as well so it's clear for the examiner. I'm going to, of course, times this value of 1.43 times 10 to the power of minus 3. And don't forget that's ... And I'm going to times that by 2 itself. I do that and I end up with a value of 2.87 ... times 10 to the power of minus 3. Of course, that's how many moles I've got of my HY acid. Now that's how many moles I've got in 25 centimeters cubed. We're about 250 instead. If the concentration is the same throughout, well, to find the number of moles of HY, but this time in 250 centimeters cubed, what I need to do is first of all, I take my number of moles of 2.87 ... times 10 to the power of minus 3. And I'm going to divide that by 25 now, because that's the volume I've got. I find how many moles I've got. I've got 1 centimeter cubed, and then I'm going to times that by 250, and so that would give me the moles in 250 centimeters cubed. I do that and I put that in my calculator and I end up with 0.0287 ... and that's how many moles I've got. And then of course I keep that in my calculator, and then I'm going to find the actual MR of HY. How am I going to do that? Well, I've been given the mass. I've also been given now the number of moles of HY that I originally got, that I've dissolved to make the total volume of 250 centimeters cubed. And so in that case we just do mass over moles. So I've got 2.794 divided by 0.0287 ... and then I end up with 97.0 itself, and the units in this case is grams per mole. And there's our 4-mark question done. Moving on, let's have a look at another question then. Again, feel free to pause the video and have a go at the following. So yeah, in this question we're told a student repeats the titration to determine the molar mass and structure of A. We're told that the student prepares 250 centimeters cube solution from 1.513 grams of A, and then the solution of A is added to the burette and titrated with 25 centimeters cubed volumes of 0.112 mole per decimeter cubed of sodium hydroxide. We're told here the molar ratio of A with sodium hydroxide, and the student obtains a mean titer value as being that. We're asked to calculate the molar mass of A again, and we need to give our answer to the nearest whole number. So of course the first thing that I need to look at over here is of course I've got a mass of 1.513 grams of A, and we dissolve that to make a kind of solution which is going to be about 250 centimeters cubed again. And then we're going to take a portion of that, which is going to be 27.30, because we're told A is going to be in the actual solution itself. It's going to be the 250 centimeter cube solution, and we're told that it's added to the burette, and that's got a variable titer value, which of course is 27.30, right? So yeah, we react that with 25 centimeters cubed and then a concentration of 0.112 mole per decimeter cubed of sodium hydroxide. So in that case we've got step 1 there, molar ratio step 2, because we're told 1 mole of A reacts with 2 moles of sodium hydroxide. The back titration step 3, and then finding the MR of our compound is step 4. So again we do the same thing again. So to find the number of moles of sodium hydroxide this time, all I'm going to do is take the concentration times by the volume, 0.112 times by 25 over 1,000, and that gives me a value of 2.80 times 10 to the power of minus 3. That's how many moles I've got. Now we're told here we've got a 1 to 2 ratio, so we know in terms of A reacting with sodium hydroxide, we're going to have 2 moles of sodium hydroxide this time, so it's going to be flipped for 1 mole of A. So in that case, to find the number of moles of A, but we know it's going to be in a volume of 27.3 centimeters cubed, we're going to take, of course, the number of moles of sodium hydroxide, which is 2.80 times 10 to the power of minus 3. And then, of course, we're going to divide that by 2. So I divide all of that by 2, and I end up with 1.40 times 10 to the power of minus 3. And then, of course, that's going to be moles again, isn't it? Now, we found the moles of our A. We now need to find the moles in 250 centimeters cubed. So the number of moles of A in 250 centimeters cubed is going to be equal to, of course, because we've got 27.30, I'm going to take my number of moles of A, which is 1.40 times 10 to the power of minus 3, and divide that by 27.30, and then times that by the original volume, which is 250. What I end up with is 0.0128 ... That's how many moles I've got. Now, of course, we found the moles. We know that many moles is going to exist in 250 centimeters cubed, and it's going to exist in 1.513 grams of A. So we know to find the MR of A, all we're going to do is take the mass divided by the moles. So I've got 1.513 divided by 0.0128 ... And then I'm going to end up with 118 grams per moles itself. So in that case, I get 1 mark here, 1 mark here, 1 mark here, and 1 mark there as well, giving our answer to 3 significant figures. But more importantly, this question actually wants it to the nearest whole number itself. Looking at our last question then, feel free to have a go at the following. Pause the video and resume once you're ready to go over it. So yeah, we're told here a student carries out an experiment to identify an unknown carbonate M, which has a mass of 1.58 grams. So we know so far the information is that we've got carbonate M. So we've got metal carbonate, and then it's got a mass of 1.58 grams. They dissolve it again into a volume of 250 centimeters cubed. So yes, I end up with my solution again, and we've got a volume of 250. We're told that the student carries out a titration using 25 centimeters cubed of this solution, and that's going to be measured using a pipette with 0.1 mole per decimeter cubed of hydrochloric acid in the burette. So in that case, that's going to go in our conical flask in this case, because remember, it could go in the burette, could go in the conical flask, but normally the bases go in the conical flask. And so yeah, we have got 25 centimeters cubed of this solution. And then we're told that our solution here is going to react with hydrochloric acid. It's going to react with 0.1 mole per decimeter cubed of that as well. And it's going to be 22.20 as a volume of hydrochloric acid as well. And we know that because it says that they find that 22.2 centimeters cubed of HCl is required for neutralization. We can see here we've got a ratio which is going to be 1 to 2. And we're asked to calculate the molar mass of M and deduce a molecular formula of M2CO3. So we know straight away, based on this, we've got M+, we've got M+, and then we've got CO3 2-. So we know it must be a group 1 carbonate itself. So if we were to look at this, the first thing that we need to do is find the moles of HCl, find the moles of our metal carbonate, find the moles of metal carbonate in 250 centimeters cubed, and then we can find the actual MR using this mass here and the moles that we calculate, and then we just need to suggest something from the periodic table. So yeah, to find the number of moles of HCl, what I'm going to do is I'm going to take my concentration of 0.1 times it by my volume of 22.20 over 1,000, of course, and what I end up with is a value of 2.22 times 10 to the power of minus 3 moles of HCl. Now in the next step, you've got a 2-to-1 ratio between HCl and your metal carbonate. So in that case, to find the moles of M2CO3, we know that we're going to take a 2-to-1 ratio, so I'm going to divide that number by 2. So I end up with 2.22 times 10 to the power of minus 3, and I'm going to divide that by 2. And what that gives me is 1.11 times 10 to the power of minus 3 moles. But remember, that's going to be in 25 centimeters cubed. So I'm going to put that down below here. So I've got 25 centimeters cubed. What about if I were to look at the number of moles of our metal carbonate? But this time, we're going to look at it in terms of 250 centimeters cubed. Well, I'm going to have over here 1.11 times 10 to the power of minus 3. Divide that by 25 because that's our volume of solution that's reacting, and then times it by 250 to scale up and find the number of moles in the original solution. I do that and I end up with, of course, 1.11 times 10 to the power of minus 2, and that's going to be moles as well. Now, of course, the next step is to find the actual MR of our compound of our metal carbonate itself. And the next step involves me taking the mass of 1.58 and dividing that by, of course, the number of moles that we just calculated, 1.11 times 10 to the power of minus 2. And then I do that, put in my calculator, and I end up with a value of 142 itself. So there is my grams per mole, but we're not finished yet, because we look at that value and we think, okay, I've got a group 2 metal carbonate, so we know that carbonate itself is going to have an MR of 12 added to 16 times 3, so in that case that is going to be 60. So to find the 2 lots of metal that we've got in there, 2 lots of group 2 metal, I'm going to do 142 subtract 60, and that leaves me with 82 left over. And then to find 1 metal, I'm going to divide both sides by 2, so that's going to be 82 divided by 2, and that ends up being 41. So I look at my periodic table and I look for a value, right, in terms of what my mass number could be. The closest thing that we can actually get is potassium in this case, right, having a value close to 41, 39.1, but remember it's experimental, so there will be some error. Can't be calcium because that's in group 2, and the formula of calcium will just be MCO3, but in this case, because we got M2CO3, we know that our answer must actually be potassium. And then it's going to be carbonate itself as well, because we've got 2 lots in there. And there's your final mark over there.